Today, we're doing something really cool. We're going to build a bridge between two worlds of math that seem totally different, formal logic and abstract algebra. And we're going to see how a tool from one can solve a really deep, fundamental problem in the other. It's all about making our understanding of truth itself more elegant, more direct. So let's dive in.
But first, let me ask you something. What makes a mathematical proof elegant? Seriously, think about it. It's kind of like looking at a map, right? You could take this long, winding, scenic route to get where you're going, or you could take the most direct path. An elegant proof is that direct path. It's simple, it's clear, and it gets straight to the point with zero unnecessary detours.
So here's our roadmap for today. We'll start with this quest for the perfect proof. Then we'll talk about the biggest obstacle logicians run into, something called the cut. And after that, we'll reveal how this brilliant bridge to algebra gives us the solution. We'll see it in action and then wrap up with why this whole connection is so incredibly insightful. At the heart of our story is this quest. For literally centuries, mathematicians and logicians haven't just been looking for proofs that are correct. They've been searching for proofs that are perfect. You know, the ones that are as clean, efficient, and just plain insightful as they can possibly be. Now, the biggest roadblock on this quest, the main thing that makes proofs messy and full of those detours, has a name. It's called the cut. So let's get a handle on what exactly we're up against here. So what is a cut? Well, it's basically a piece of a proof that introduces a temporary and often complicated sidestep. It's like saying, to prove A leads to C, first let's prove this completely other thing, B, and then we'll show how B gets us to C. I mean, it works, sure, but it's not direct. It's a logical detour that can make the whole argument super complex and hide what's really going on. And the difference is just night and day. Look at this. On the left, a proof with cuts is that rambling journey. It's cluttered, it gets you there, but it's a mess. On the right, though, a cut-free proof is a clean, direct highway. It only uses pieces that were already part of the original puzzle. And this isn't just about being tidy. Getting rid of cuts actually reveals the essential, beautiful structure of the argument itself. And as you might guess, the process of cleaning up these proofs has a name: cut elimination. It's a formal way of systematically going through a proof, finding every single one of these detours and getting rid of them, turning a clunky argument into that beautiful, direct path to the truth. Okay, so this all sounds great if you're a mathematician who loves elegance. But so what? Does this really matter for the rest of us? Why is getting rid of these detours so important? Well, it turns out the consequences are absolutely massive. The answer is this is a cornerstone of modern logic and computer science. For starters, it's how you prove a logical system is consistent, that it won't ever contradict itself, which is kind of a big deal. From there, the benefits just keep coming. It makes it way easier for computers to search for proofs automatically. You can even use it to build software directly from a proof. This is not just tidying up, this is fundamental stuff. Now, here's the catch. Proving that cut elimination actually works for any given logical system can be incredibly difficult, just a tangled mess. But recently, logicians have found a powerful new way to tackle this old problem. They've built an algebraic bridge. And here's the core idea behind it. Instead of getting bogged down in all the messy details of logical symbols and rules, we can use the structure and power of algebra to simplify and clarify the entire process. It's a total game changer in terms of perspective. Think of it this way. You've got two different lands, right? Logic is the land of propositions and inferences. Algebra is the land of equations and structures. By building this bridge, we can take a problem from the land of logic, translate it into the language of algebra, solve it there with all these powerful algebraic tools, and then bring the solution back. It's brilliant. So what does this actually look like in practice? How does algebra really help untangle all these logical knots? Let's take a quick peek inside the algebraic toolbox. Okay, don't worry about memorizing all these names. The key takeaway here is that this isn't just one single trick. It's a whole toolbox full of different tools for different jobs. For example, things called residuated lattices are perfect for logics where the order of things matters. Others, like display logic, are built to handle ideas like time or possibility. The point is, there's a whole world of these powerful algebraic methods, each one tailored for a specific job. All right, so we've seen the problem, the cut, and we've seen the solution, the algebraic bridge.
So what's the ultimate payoff here? What do we get out of all this? Well, it all boils down to two things: simpler proofs and much, much deeper insights.
Here's how it works, in 3 steps. First, algebra abstracts the problem. It lifts it out of all the nitty-gritty details into a much cleaner, higher-level view. Second, it systematizes the solution. Logicians can create general recipes for building these cut-free systems instead of starting from scratch every single time. And finally, it unifies our understanding. It reveals these deep, almost harmonious connections between different logical rules that we never saw before. And I really want to stress this. This is not just some abstract exercise to make things look prettier on a blackboard. This algebraic perspective leads directly to new, powerful, and very concrete algorithms that have real applications. Here's a perfect example. There's this new algorithm called unthreading. See, normally when you eliminate cuts, the proof can sometimes explode in size temporarily before it shrinks down. It's a huge headache. But this new method, inspired by algebra, guarantees that the proof gets smaller at every single step. No explosions. That is a massive leap forward in efficiency. And really, this brings us to the main takeaway. By taking the problems of logic and reframing them in the language of algebra, we get this incredibly powerful new perspective. This fresh point of view lets us see hidden structures that were there all along, leading us to solutions that aren't just correct, they're truly elegant. And that leaves us with a final thought to chew on. If building a bridge from algebra over to logic can so fundamentally change our understanding of something as basic as proof and truth, it really makes you wonder, doesn't it? What other incredible discoveries are just sitting there, waiting for us to build the right bridge between two different fields of knowledge? What other hidden structures are we missing just because we haven't found the right language to see them yet?